Assalamualaikum and good evening. First, I bid to Dr. Halim, uh, my lecturer for STP subject. And for today, I want to present to you about my technical review presentation about the swell noise attenuation. First of all, the abstract for this topic is about the noise attenuation that for ordinary image using a machine learning has achieved a great success in the computer vision field. And however, directly applying this model of seismic data will not be effective since the evaluation criteria from the geophysical domain require a high quality visualized image and the ability to maintain the original seismic signal from the contaminated wavelet. Thus, there are several models that believe to effectively remove a swell noise. So first of all, the definition of the swell noise. The swell noise is caused by the long period changes in the ocean surface, and it is the type of the incoherent noise characterized by low frequencies and high amplitude switches. And the swell noise attenuation are usually the first step when it comes to the marine seismic data, and it's produced by the high amplitude ranging from 2 to 10 Hz. So the objective of this study is to maintain the visual quality of the seismic image and the recovery quality of the seismic signal, and is to gain the better denoising result in terms of noise detection and primary protection. And thirdly is the innovative approach on the automation of noise detection step to remove a swell noise. So for the lecture review consists of five elements that we want to discuss is first is the main people working in the area, and second is the recent major advances and discovery. Third is significant gaps in the research. Fourth is the current debates, and lastly is the ideas where the research might go next. So there are three main people working in the areas, which in 1983, Peacock stated that the two different mechanisms that create a swell noise on fluid streamers that the streamer's motion can induce a transversal wave. And in 2001, Yilmaz stated that most of the methods developed to initiate high amplitude swell noise based on the rejection of the low frequency band of the recorded data. And lastly, in 2009, the swell noise is the most dominant noise type on the raw marine short girders and mainly originated from the rough sea state due to the weather condition which produce a wind-driven longitudinal sea surface wave and can be regarded as incoherent noise uh, in marine data sets. And the two important key is the hydrostatic pressure fluctuation and the dynamic pressure variation. The hydrostatic pressure fluctuation due to the vertical motion of the ocean because of the weather condition, while the dynamic pressure variation along the streamer due to the turbulent layer surrounding the streamer. So for the recent major advances and discoveries are divided it into three categories, which is the automatic swell noise automation process, continuous wavelet transform, and the conventional method. So for the automatic swell noise attenuation process, the only noise location are filtered and deriving a global FX signal mask for each gather, which the finding traces are contaminated with swell noise and which the frequency in those contaminated traces the noise is present. And noise detection is done globally. It is disjointed from the noise filtering step, so there is no trade-off terms of finding good parameterization and the possibility to adapt the spatial window size for the filtering as function of frequency for a better signal interpolation. And the derivation of the signal mask is done over a portion of the gather where the signal to swell noise level is low. So for the continuous wavelet transform or CWT, is function to develop the filter that can eliminate coherent low frequency noises like swell noise without impacting parts of the data that inversion schemes are required. And the continuous wavelet transform is proposed in this work for achieving effective localized frequency band filtering for swell noise attenuation. and by constructing filter based on the wavelet transform for suitable set of wavelet and scales. And next, we apply the continuous wavelet transform to the seismogram, which means convolving each trace with the modeled wavelet at many scales. And this operation increases the dimensionality of the dataset, as each seismic trace is now represented as a two-dimensional panel. So we can apply the same procedure to both real and synthetic dataset, which allows to produce the continuous wavelet transform panels representing our ideal output, and then create a mask in the continuous wavelet transform domain to filter out undesired event in the real datasets. So for the conventional method, a band pass filter cannot eliminate swell noise without also eliminating significant portion of the seismic reflection signal. So we discovered, uh, stated by the Elboth and the Beccara, they discovered the time frequency filtering, and it works by computing a spectral approximation at its frequency, which is then compared to the amplitude of a presumed successful trace in a given window. The amplitude would be attenuated to the level of a supposed successful trace. If it is greater, then it will be repeated for all frequencies specified by user and changed back to the time domain for each sliding window. And it is important that the window size is not too wide in order to achieve the best result. So first, the significant gaps in the research that I found that is stacking in the wavelet packet domain in 1999, where the stack data in the wavelet packet domain after removing wavelet coefficient that contribute to a low coherency in the wavelet pocket domain. The wavelet pocket domain is localized in both frequency and time, and it is possible to target both the frequency and the time when the noise is present. So the number of the data sample in the problem area is reduced, and processing time may be optimized by judicious selection of the wavelet packet decomposition. Because the wavelet packet transform is not shift invariant, we must carry out the processing on the CDP gathers that are corrected for NMO. So the future work should concentrate on the understanding the complete implication of a time shift in the wavelet packet domain and incorporating things in algorithm. Next is in 2011, swell noise suppression by linear prediction filter. So in terms of eliminating swell noise, the WPF approach can be considered as an alternative to the conventional BPF filter. And the application shows that the method eliminates the majority of the swell noise from raw seismic data while preserving the deeper reflection amplitudes and thereby expanding the frequency band available. So as compared to the conventional BPF data, the deeper reflection have a higher amplitudes and stronger lateral continuity in the final migration section obtained by the WPF application. So suggestion involve using the approach to eliminate other form of coherent noise if an effective noise model can be defined. So next is the Swell noise attenuation, a deep learning approach in 2019. So applying FX filtering to the frequency spectrum where the noise is present and replacing the noisy traces with their FX filter version for this frequency is a simple solution to a swell noise attenuation. So as stated by a few authors in 2005, 2009, and 2012, a deep learning in the denoising task for image has been developed in the past decades, and many research works indicate that made a giant leap in this field. And it's also introduced an improvement by applying FX filtering iteratively. And Beccara and Van also stated that develop an automatic method to exploit differences in statistical properties between swell noise and signal amplitude to construct a detection criterion. So for the current debates in chronological order, in 1999, Watt stated that it demonstrates how the wavelet packet domain processing in marine data can minimize a wave swell noise. So they stack the data in the wavelet packet domain after removing wavelet coefficient that cause the low coherency in the wavelet packet domain. So the processing in the wavelet packet domain has the advantage of being able to target both the frequencies and the time when the noise is present. So in 2009, Albert stated that the article stated that and demonstrate how time frequency denoising can be used in marine seismic to reduce many of the most common form of noise. The general idea is to isolate uh, each form of noise in a domain where it stands out and then reduce it. And later in 2009, Zhao proposed a deep learning model for a seismic swell noise attenuation, which called only two noise, is applied to a synthetic dataset and a field dataset. So when opposed to a conventional method, it yields outcomes that are extremely comparable. The only two noise easily and greatly improve the raw data quality with a simple uplift. So based on the detailed and careful review of the frequency panel, typical panel, and stacking efficiency, the model indicates that the swell noise has been effectively detected and removed mild primary hertz. So this next is the ideas where the research might go next. I divided it also in three categories by three different authors: Donduro and Kasley in 2012, Tomuno, Beraton, Amakri, and Murray in 2015, and Alves in 2019. So Donduro and Kasley stated that in terms of eliminating swell noise, the WPF approach can be considered an alternative to the conventional BPF filter. The application demonstrates that the system effectively eliminates the bulk of swell noise from raw seismic data while maintaining the deeper reflection amplitudes. And later in 2015, uh, the time frequency algorithm have been shown to be an efficient method for attenuating a variety of noise energy from seismic gathers in the marine environment, and swell noise complexity can be solved. It affirms the reliability of the approach and the validity of the outcome. And lastly, Alves in 2019 stated that using a continuous wavelet transform, a workflow for constructing and applying a coherent noise filter. It demonstrates that this approach can effectively attenuate swell noise in the data without the use of Fourier space low cut frequency filter, which could impact low frequency of useful data. So for the current issue, I choose the deep learning approach by Zhao in December 2019, which stated that as you all know, that directly applying this model to seismic data were not effective since the evaluation criteria from the geophysical domain require a high quality visualized image and the ability to maintain the original seismic signal from the contaminated wavelet. So there is an approach equipped with a specifically designed deep learning model that can effectively attenuate swell noise with different intensity and characteristic from short gathers with a relatively simple workflow applicable to marine seismic datasets. And the proposed deep learning approach can be considered as an alternative approach that combines and takes advantage of both conventional and data-driven methods to better serve swell noise attenuation, and to share a deep learning based solution for swell noise automation by directly training a swell noise model. And as such, swell noise model can be derived from any marine data by using a conventional algorithm. Effectively and efficiently training on even a contaminated swell noise model guaranteed and improved performance of attenuating swell noise from raw data. And such method, in combination with a conventional and data-driven algorithm, introduce a new means with a strong potential to solve attenuation tasks relevant to swell noise as well as other coherent noise. So, to conclude, it is essential to denoise seismic data in order to obtain a high-quality seismic bits, and this denoising mix was engineered to target a low-frequency swell noise with extremely large amplitude as well as a random noise. And even on the polluted swell noise models, effective and efficient training ensures improved performance of attenuating swell noise from raw data. And this method, when combined with a conventional and data-driven algorithm, incorporates new method for solving attenuation tasks involving a swell noise and other coherent noise. So that's all for the technical my technical review presentation, and thank you for listening.